Okay, let's get started. Today we are going to talk about the asymptotics in the test. Uh, so this is the contents of the chapter 10 after the point estimation. So we would like to discuss likelihood ratio test, word test, and score test. First, let me talk about the likelihood ratio test. So if you recall the usual likelihood ratio test statistic, so the likelihood ratio test statistic is ratio of two likelihoods. Uh, the likelihood in the denominator is likelihood in the numerator is the supremum of the likelihood value under the null hypothesis, and likelihood in the denominator is the supremum of the likelihood value under the in the entire parameter space. Then we can construct the likelihood ratio test based on likelihood ratio test statistic. So the likelihood ratio level alpha test procedure is we reject H0 if and only if the lambda is less than or equal to C, where C is chosen such that the supremum probability that the lambda x is less than or equal to C under the null hypothesis is the less than equal to alpha. So and if you recall that, to record the likelihood I mean likelihood ratio test procedure, one needs to so so the first step to construct the likelihood ratio test is the find the restricted MLE uh, for theta in the omega 0. So under the null hypothesis, we need to find the restricted maximum likelihood estimator. And the second step is to find the maximum likelihood estimator under theta is in the omega. I mean, when theta is in entire parameter space, we need to find the maximum likelihood estimator. And we need to derive distribution of the lambda x or distribution of the function of the lambda x. And this solve star. I mean, star is the supremum of the probability that the lambda x is less than or equal to c under the null hypothesis is less than or equal to alpha, and then so we solve the star to get the c. However, usually finding exact distribution of lambda x is very difficult, and so getting c is also difficult. However, if we have large sample size, we can get approximate distribution of the function of lambda x, so we can test. We can do a test easily. So consider testing theta equals theta 0 versus theta is not equal to theta 0. So suppose that we have IID random sample and theta hat is the emitter of theta, then the PDF of X satisfy the certain regularity conditions which are described in the Miscelina 10.6.2. So if we have the conditions, then under the null hypothesis, -2 times log of the likelihood ratio test statistic converges in distribution to chi-square distribution with 1 degree of freedom as n goes to infinity. So it means that when sample size is getting large, -2 times log of the likelihood ratio test statistic is approximately distributed as chi-square with 1 degree of freedom. So proof is that -2 times log of lambda x is equal to minus 2 times log likelihood of theta 0 given x plus 2 times log likelihood of theta hat given x tilde. So this L is this little L is the log likelihood. And then now we would like to expand this log likelihood theta given x tilde around theta hat. So in studying our asymptotics, Taylor series expansion is the most useful and important tool. So we would like to do a Taylor expansion. So if we explain this log likelihood around theta hat, we can get L sub theta hat given x plus L prime theta hat given x tilde times theta minus theta hat plus L prime prime theta hat given x tilde and theta minus theta hat divided by 2. Theta minus theta hat squared divided by 2 plus remainder. Remainder term we can ignore. Then we know that this L prime theta hat given x tilde is equal to 0 because we can get the theta hat by setting the L prime theta given x tilde equal to 0. So this is the, if you remember, this is the score function. So if you we get the theta hat by setting this score function or derivative of L theta is equal to 0. So if you plug in theta hat this derivative of log likelihood, then we get the equal to 0. So this gives this L prime prime theta hat given x tilde times theta 0 minus theta hat squared divided by 2 plus the L theta hat given x. So because this term goes away, so we only have this term. Then we so we can approximate the L sub theta 0 given x tilde. Then log of lambda x tilde is. So remember that the minus 2 times log lambda tilde is the minus 2 times log minus 2 times the log likelihood under theta 0 plus 2 times the likelihood under the unrestricted MLE. So we get this is equal to so this is the definition, and then if this is approximate to by plugging in this expression to here, so we can get the theta 0 minus theta hat square times minus the second derivative of the log likelihood under the theta hat. Then so theta hat is MLE under the null hypothesis. Theta hat is asymptotically normal with the mean theta 0 and the variance 1 divided by information number for entire sample under theta 0. And then this minus second derivative of the log likelihood and minus is the observed information number. So this observed information number divided by n converges in probability to a single information number. So for that convergence, we need a strong regularity condition, but we assume that we have. So under that assumption, the observed information number divided by n converges in probability to the single information number under theta 0. So we have these two conditions. Then for this, from these two conditions, we have so by first start, this theta hat minus theta 0 times square root of the entire observational number under theta 0, it converges in distribution to the standard normal distribution. Then by continuous mapping theorem, if you square the left-hand side, that converges in distribution to the chi-square distribution with 1 degree of freedom, which is the square of the standard normal distribution. Then you can see that we have this expression. This is we just multiply by this the in theta 0 and divide by in theta 0. Times and also multiply by 1 over n, divide by 1 over n. And then this term, so we don't do anything new, we just multiply in theta 0 and divide by in theta 0, and also multiply 1 over n, divide by 1 over n in this original equation. Then this square term converges probably to 1. So let me write it again. So converges probably 1 by the second expression, second star, because in the 2 star, 1 over n times the minus observed information number conversion probability to in theta 0. I theta 0, and in theta 0 is entire observation number. So we have IID, so this is n times I theta 0, n times the single information number. So this 1 over n times the observed information number converges into the 1 over n times the entire integration number under theta 0. So by division, so this ratio converges in probability to 1. And by Slutsky's theorem, so we have term that converges in probability to 1, and we have a term that converges in distribution. So this term converges in distribution to the chi-square 1, and then this next term converges in probability to 1. So we can use the Slutsky's theorem. This entire term, theta hat minus theta 0 squared times the minus information observed information number converges in distribution to chi-square distribution with degrees of freedom 1, which gives minus 2 times log of lambda x tilde, minus 2 times log of the likelihood ratio test statistic converges in distribution to chi-square distribution with degrees of freedom 1. So let me give an example. So we would like to find the log likelihood ratio test when we have a Poisson random sample, and we would like to test lambda equal to lambda 0 versus the lambda is not equal to lambda 0. So you can easily see that the M area of lambda is x bar. Then we can have the likelihood ratio test statistic would be, so in the numerator is the under null hypothesis, so we find the likelihood function under lambda 0. In the denominator, so unrestricted MLE is the x bar, so we would like to find the likelihood function value under x bar. We have this ratio value, and then this is equal to we have e to the power minus n times lambda 0 minus x bar times lambda 0 divided by x bar power sum of xi. Then so if you take a log on the first, there's the likelihood ratio test statistic. So we can so take a log that gives the first term, it would be minus n times lambda 0 minus x bar. Next term is the sum of xi times log lambda 0 minus log of x bar. And then we multiply the entire term by minus 2. This is you can rearrange this term by 2n times lambda 0 minus x bar times log of lambda 0 divided by x bar is approximately distributed by chi-square distribution with 1 degree of freedom. So level alpha test is so this is probability under the lambda 0, so minus 2 times log of lambda x is greater than c is equal to alpha. So we can take c as chi-square distribution with the 1 minus alpha percentile of the chi-square distribution with 1 degree of freedom. So if we have chi-square distribution of freedom, then is the 100 times 1 minus alpha percentile is the area under curve after value of the 1 minus 100% times 1 minus alpha percentile is the alpha. So this means that is the one probability that the chi-square distribution is greater than the chi-square distribution with the with degrees of freedom 1 and the let me back up. So the probability that the chi-square distribution with degrees of freedom is greater than the 100 times 1 minus alpha percentile of the chi-square distribution with 1 degree of freedom, that probability is equal to alpha. So we check. We check H0 if and only if minus 2 times log of the lambda x is the greater than chi-square distribution with the greater than the 100 times 1 minus alpha percentile value of chi-square distribution with 1 degree of freedom.